All right, so we're moving on to chapter 11 after briefly going back to chapter 4. Chapter 11 is inferences on two samples, which is basically just hypothesis testing for two parameters. We start with 11.1, which is inference about two population proportions. Which is really just a fancy way of saying we're going to be hypothesis testing for two proportions at the same time. So in chapter 10, if you remember, there was a claim about a proportion, that the true proportion is equal to something, and then we go out, we get a sample, and then that sample is either enough evidence to refute that claim or reject HO, the null hypothesis, or it's not sufficient evidence against the null, and we fail to reject the null. In this case, we're going to have two population proportions. So let me write this down in this section. We will hypothesis test two proportions simultaneously. So at the same time, right? The proportions will be sort of related to one another. We don't want to hypothesis test two proportions at the same time if they have nothing to do with one another. If they measure different things, like proportion of people who smoke cigarettes and proportion of people who will pass my class, that's not something anyone would ever be interested in both at the same time for. So the proportions will be related in the sense, or in effect, we will be testing their relationship to one another. For example, are they the same? Is one greater than the other? Or is one, oops, I shouldn't say smaller, I should talk like a mathematician, is one less than the other? So a real life example would be, that comes up a lot, and you'll see if you follow along with the book, or actually any stats book really, and the examples in this kind of section, a big thing that people are interested in is the differences between the genders, between men and women. So for instance, are men more likely to smoke cigarettes than women? That would be an example where we would have to basically hypothesis test two proportions at the same time, right? Because in essence, there is a P for men. That would be the proportion of men who smoke. And there would be a PW, I guess, which would be the proportion of women who smoke. Right? So in the last section, well, actually, I should say in chapter 10, we only really were interested in one proportion that we don't know the true value of, right? At a time. So like the proportion of people who smoke, period. And we are curious what that is, and we test to see if there's, I think there was a claim made, and we test to see if that claim was accurate. We could also construct confidence intervals and stuff. But in this section, we're going to be interested in two related proportions: the proportion of men who smoke, what percent of men smoke, versus what percent of women smoke. Is one bigger than the other? Do men smoke more often than women? Do women smoke more often than men? Or are they about the same? I have no idea, but that's exactly the type of problem that would be in this section, is comparing these two things. We don't know what the true proportion is for either one, right? And so what's going to happen is we're going to have to hypothesis test these two things to see if there's a difference between them, is really what it's going to boil down to. There's going to be a lot of notation in this. In this section that you may see. So things like P1 and P2. These are maybe I should put them closer together. P1 and P2 are the two parameters, right? We don't know those. The true values of, let's say I labeled them with an M and a W up here, right? The true proportion of men that smoke and the true proportion of women that smoke. We don't actually know what those are. To get those, we would have to talk to everyone in the world. We know that we can't get those. So what do we always resort to? We resort to statistics, right? So we'll have a P1 hat and P2 hat are the what? Two statistics, right? Two statistics. Right? You're going to have to go out there and get a sample on your own, right? If there could be a claim, the true proportion of men that smoke is, I don't know, 12%, but then your sample that you go out and get as evidence, it might result in 12% or something, right? So here's the notation for the parameters, here's the notation for the statistics. What else do we have? Well, we have N1 and N2, which are the sample sizes. We would have X1 and X2 are the number of successes. I guess since we have P1 and P2, we could have Q1 and Q2, right? Basically, we're doubling up on all of the notation that we've already had, right? These are the failure rates. I'm just trying to illustrate the fact that we're going to be doing two things at once, right? So whereas hypothesis testing before, we only dealt with P, P hat, N, X, and Q hat at the same time. We're doubling up our work because we're dealing with two parameters at the same time. In my example, the true proportion of men who smoke, and then all of our statistical variables here, everything that came from our sample, and then also the true proportion of women that smoke, and then also we have a sample of women to test that. And so what's going to happen is the math, if we want to do this by hand, the math tends to get pretty hard. So before I even get into how do we set up hypotheses or anything like that, I kind of want to show you first some of the stuff that we would be getting into if we start tackling this by hand. In class, I would probably put don't write this down because I'm really just kind of illustrating a point here. But when we are hypothesis testing proportions, one of the steps was to come up with a z-score, right? That would also be a part of hypothesis testing two proportions at a time, is to come up with a z-score. And I'm just going to show you what the z-score formula looks like for hypothesis testing two proportions at one time. Oops, look, I already messed up. That's not good. But the z-score formula for hypothesis testing two proportions at once is this. P1 hat minus P2 hat minus P1 minus P2 divided by big square root. That's never a good sign when you hear that, right? P bar Q bar over N1 plus P bar Q bar over N2. And this is just the formula for the z-score. And you can see why I would probably want to avoid that. So I'm going to make a note. I wouldn't want to do this. So we will use StatCrunch. So if you enjoyed the Chapter 4 stuff where we were kind of forced to use StatCrunch because of the crappy formulas that we would have to use if we wanted to do it by hand, if you enjoyed Chapter 4, you enjoyed using StatCrunch, then maybe you'll enjoy this section. We're basically not going to do any handwritten math in this section. All these weird variables we don't really need. We don't need formulas like this either because StatCrunch is going to be doing all the work for us for these type of problems behind the scenes. So let's kind of ignore all this nonsense and jump straight to how do we actually use StatCrunch, right? What are we actually doing? How can we use StatCrunch if we're not going to be using, I don't want to say real math, because StatCrunch is also using real math, but I don't want to take the long way. I don't want to have to be bogged down by something like that, right? So how do we use StatCrunch? All right, well, let me write the steps. To hypothesis test, two proportions using StatCrunch. Maybe put that in parentheses. So to hypothesis test two proportions, the first step is set up HO and HA. That should be no surprise. That's what we did in Chapter 10. That's what we did in Chapter 4. That's what we're going to be doing in Chapter 11. The first step is to set up the hypotheses. If you go back and watch my lecture for Chapter 10, I even say, like, this is an important part, and here's why. It comes up constantly, right? So HO, oh, maybe I make a note. The null hypothesis, HO, will always be the same. HO will be that the true proportion of your first subset, like men, smokers, is equal to the true proportion of the other subset, like women smokers. Or the true proportion of people who get better using this new drug versus the proportion of people who get better just with bed rest or something, right? If those two proportions are equal, then we don't need to go with the drug, right? So your null hypothesis is that always that these two proportions are the same, that P1 equals P2. This is always going to be the null hypothesis for these types of problems. What is the alternate? HA will be the same as HO, but with a less than sign, a greater than sign, or a not equal to sign. So the possible HAs are HA P1 is less than P2. HA could also be P1 is greater than P2, or HA could be set up as P1 is just not equal to P2, right? And these depend on the problem, right? The problem will say test if the proportion of men who smoke is actually greater than. Well, then you would set it up like this, right? Greater than the proportion of women that smoke. Or test that the proportion of people who die while taking this drug is less than the proportion of people who die when they're not taking medicine. Or if you're just interested, are the proportions themselves just different from one another, then you can set it up with not equal to, right? What sign you set HA up with is going to depend on the context of the problem, and it's usually pretty clear. I'm not going to try to trick you or anything. The only thing is that StatCrunch, for some reason, uses different notation when they have the hypothesis set up. For the null hypothesis, they have it as P1 minus P2 equals 0, which is the same thing. I hope you guys can see that if you subtract P2 from both sides of this, you would have P1 minus P2 equals 0 would be left over on the other side. These are two of the same way. These are two ways of writing the same exact thing. That the two proportions are the same is the same thing as if you subtract them, you get 0, right? The only way you get 0 after subtracting two things is if they're equal to one another. So these two things mean the same thing. And for some reason, StatCrunch likes showing it like this, how I have in red. And StatCrunch does the same thing for these other hypotheses. Instead of having HA P1 is less than P2, they have it as P1 minus P2 is less than 0. They're really just moving the P2 to the other side. HA could be P1 minus P2 is greater than 0, and HA could be P1, oops, look at me getting carried away. P1 minus P2 is not equal to 0. They're really, I don't know why StatCrunch kind of sets it up like this, but they set up the hypotheses like they have in red, which are fine, because all they're doing is moving the P2 to the other side with the P1 in each of these, right? They're just moving it over and comparing it to 0. But I like setting it up the way I have it in black. If you set it up the way that StatCrunch does, it's perfectly fine. So set up your hypotheses would be the first step. Second step would be use StatCrunch. And here are the steps to use StatCrunch. You need to go into the Stat menu. It's up at the top. I'll show you in an example later. After you go into the Stat menu, you go down to Proportion Stats. After you click on Proportion Stats, it brings up another menu. You will choose ToSample. After you choose ToSample, you have to choose With Summary. And that'll bring up the menu we need. In this menu, enter all information from the problem. You'll need, for sample 1, you'll need x1, n1. Oops, I don't need another comma. So in sample 1, you need x1 and n1. In sample 2, you'll see this in an example, so just give me a second to get this all out here. In sample 2, you need x2 and n2. And the hypothesis testing, the hypotheses. Meaning what inequality HA has. So was it a less than, greater than, or not equal to? And just so that you guys remember, what are x1 and n1? These are the total number of successes you found in the first sample out of how many was sampled, total number of observations, right? And then you have a second sample in the same problem. How many successes did you get there compared to how many did you sample there? You enter those into StatCrunch. There's places to enter this. Again, I'll show you in a second when we do a problem. And then you also have to make sure that the HA inequality is set. Everything else should be set up like normal. StatCrunch should already be set up to be hypothesis testing at a 0.05 significance, like we have been. So there's no reason to change any of the other settings, unless you already did for some reason, but you shouldn't have. So after you put all that into StatCrunch, report the p-value. Oops. So StatCrunch will spit out, just like it did with hypothesis testing for correlation and regression, it spat out a p-value. You should have wrote that down when you were doing those. Same thing here, report the p-value that StatCrunch gives you, and then step 4 is make the conclusion. If the p-value is less than 0.05, we reject HO. If the p-value is greater than 0.05, we fail to reject. The null hypothesis. All right, and those are our steps. Let me zoom out so we can see them all together, and I can walk through them one more time. First step is to set up the hypotheses. The question will ask something like, we sampled a bunch of men and also a bunch of women, found this percent of men smoke, this percent of women smoke. Is that enough evidence to say more men smoke on average than women? You know, the proportion of male smokers is higher than the proportion of female smokers. Well, the null hypothesis would be that the true proportion of men who smoke is the same as women who smoke. This is always going to be your null, is that there's no difference between these two proportions, that they're the same. The alternate, well, I said that we're going to test, is the proportion of men who smoke greater than the proportion of women who smoke? So I would have chose this HA, that P1 is greater than P2. And then I would have opened StatCrunch, put in my information from sample 1 and sample 2, and then also make sure I have my HA to be a greater than. I would hit enter, or I think it says compute, not actually sure. And then it'll spit out a p-value, and then looking at that p-value, if it was less than 0.05, I would reject HO. I would not believe that the true proportion of men who smoke is equal to the true proportion of women that do. I would believe my alternate, that men smoke more often than women. However, if my p-value was bigger than 0.05, if it's greater, then I would fail to reject HO, meaning I would still think the proportion of men who smoke is equal to the proportion of women who smoke. I would have no reason to reject that idea. And that's it. StatCrunch is going to be doing all of the legwork for us. If you want, you can do these by hand. It's technically not impossible. It just sucks. And I'm just going to put that out there. It's not fun because the equations, there's a lot of places to mess up with like human error. If you have a book, it does walk through how to do it by hand. But I don't want to teach that since all of you are required to have StatCrunch anyway. Especially, there's no way to do correlation and regression, really, as far as I know, by hand that would keep you sane. Same thing here. You're going to want to do this in StatCrunch. So if you thought, oh, I don't want to get it, I'm going to do everything by hand, Godspeed. I'm going to do StatCrunch. So let's do an example so that you guys can see what I'm talking about. And I think I'm going to do an example from the book. I just need to find a good one to do, something at least that's interesting. They really make their problems crazy. All right, here we go. And this is a problem between men and women too, so it's kind of what I've been alluding to with the smoking example. Here we go. A nutritionist wants to estimate the difference between the proportion of males and females who consume the USDA's recommended, recommended daily intake of calcium. I'm going to tweak their stuff here. The nutritionist. Oops. I don't know why I keep making mistakes on writing. The nutritionist. Randomly samples. Let's say 1,900 men and 2,061 women. Of the men, oops, I jinxed myself there. Of the men, and I want to make sure this works, so I'm going to change their numbers a bit. Of the men, 971. What was the consumed the recommended amount of calcium? And of the women, how many of them? Let's see, there's 2061. Let's say of the women, 1,548 consume the recommended amount. And the question we want to answer is, does the proportion of men, or is the proportion of men, is the proportion of men who consume the recommended daily amount of calcium less than the proportion of women who do. Okay. The one thing I hate about these problems is they're so long to write out because you basically have to throw two samples in the same prompt. So thanks for hanging in there. Let me reread the question so that I can kind of understand it myself. Let's see. A nutritionist wants to estimate the difference between proportion of males and females who consume the recommended daily intake of calcium. Okay, that's just fluff. We don't really care about anything before this point, right? The nutritionist randomly samples 1,900 men, 2,061 women. Of the men, 971 ended up getting the right amount of calcium in the day, and of the women, 1,548 consumed the recommended amount. Okay, all right. And we're curious, is the proportion of men who consume the recommended daily amount of calcium less than the proportion of women who do? So is the percentage of men getting their daily recommended amount of calcium actually less in reality than the proportion of women that do? I mean, we're only using less than 4,000 people in this study, but hopefully we'll be able to say something about, is there an actual gender difference with the amount of calcium we intake? So let me label the solution. Going back to the instructions, set up HOA and HA. And like I said, HO is going to be the same no matter what. It's that the two proportions are equal. What is this saying? That the proportion of men who get their daily recommended amount of calcium is equal to the same proportion of women who get their daily recommended intake of calcium. That's a mouthful. But the proportion of men who get the amount of calcium they're supposed to have is equal to the proportion of women that do. That there's no gender difference. It's a human thing. We all get about the same amount of calcium percentage-wise. The HA is that, well, the problem asked less than, right? Is the proportion of men less than proportion for women? Is the proportion of men who get the amount of calcium that's recommended less than the percentage of women that get the daily amount of calcium recommended? Oof. This is why I hate the book. It has so much verbiage. But these are our two hypotheses, right? That there's no gender difference. The proportion of men is equal to the proportion for women. The alternate is that men, their percentage of people, the percentage of men, the percentage of men who get their recommended amount is less than the percentage of women who get their recommended amount. Oof. That's a lot of talking, but hopefully the math makes sense. The two hypotheses, at least. Step 2. Oops. I don't know why it zoomed in. Step 2. Use StatCrunch. So it says to go into the stat menu, proportion stats, to sample with summary. All right, I'll keep that in my mind. In this menu, I'm going to need all this information. Well, luckily, I already have the hypothesis set up, right? I know what the HA inequality is. In my example, the inequality is less than, because that's what the problem said. The other things I need to make sure I know are x1, n1, x2, n2. Okay, so what were they? x1 and n1 is something I need to make sure I put into StatCrunch, and so is x2, n2. So let's make sure we know those from the problem. Well, in my hypotheses, I set up 1 to be men, right? So I should be consistent. These should be the values for men. So what was the total number of observations? I always like starting with n first. Total number of observations of men. Well, the total number of observations of men is 1,900. And of those, how many successes do we have, right? That's what x1 means. How many successes did we have for the men? Well, that was 971. For the women, that's when I made the 2. For the women, the sample size and how many women did we sample? 2,061. And of those, how many successes? 1,548. That's an ugly 4. There we go. That's a little better. These were the numbers from my sample of women. And that's what these are the numbers we're going to enter in on StatCrunch. And so I'm going to switch windows for a second to go into StatCrunch, but I just want to make sure that I remember everything I need. Go to Stat menu, Proportion Stats, to Sample with Summary. That's how you get there. I only have my iPad to go on right now, so you'll hopefully be able to switch back and forth a little bit better. And then these are the numbers I'm going to put in that menu. This was my sample, the numbers I got from my sample of men. 971 was my number of successes out of 1,900. For women, it was 1,548 out of the 2,061. All right, so let's go to StatCrunch. Come on. And I believe it said go into the stat menu. Since I'm on an iPad, it looks like this. If you're on a desktop, it's like a drop-down menu. But you go into stat, and then proportion stats is right here. I already had it highlighted. So you go into proportion stats to sample right here. Again, I already had it highlighted because I was ready for the problem. And with summary. And then this menu pops up. Again, if you're on a desktop, it's like a little window. It asks number of successes. So how many was it? Number of successes for the men was 971. 971. Total number of observations made. I think was 1900. I'll double check these numbers one more time. For the women from sample 2, it was 1548 and 2061. 1548 and 2061. Right? Those are the right numbers, right? 971 and 1900 and 1548 and 2061. Just want to double check because I don't want to put in the wrong numbers, right? 971, 1900, 1548, 2061. Looks good to me. Yep. And then under perform, it says hypothesis test. It's already highlighted. We don't need to construct confidence intervals for this stuff, but it has HO. Like I said, for some reason they like having it equal to 0, everything being moved to one side, which is fine. But you see HA, it has it set up with not equal to, but we want less than. And that's it. So I'll hit compute, and a pop-up comes up. And you'll see it says the p-value over here is less than 0.00001. So this is our p-value right here. So going back, that was the step 3. I have to report the p-value. So, still red. The p-value, step 3. Said 0.000. Was it 3 zeros and then a 1? I can't remember. Oops. Oops, I went back to the notes. Yep, 3 zeros and then a 1. Oh, man. The iPad doesn't like going back and forth between apps, I guess. It actually said it was less than 0.0001, but for our purposes, that's fine. Looks like it rounded it up, but wanted to let you know it's actually even smaller than that, but that's okay. Step 4 is to make our conclusion, right? Step 4 was make the conclusion. If the p-value is small, so since the p-value 0.0001 is less than 0.05, just like before, when our p-value is small, we reject the null hypothesis. So, answering the question now, this is what usually trips students up. Is the proportion of men who consume the recommended daily amount of calcium less than the proportion of women who do? Well, after my hypothesis test, maybe I'll use purple. After my hypothesis test, I'm ending up rejecting HO, right? I do not believe this. I'm rejecting this idea, right? I believe this. Because I rejected HO, I'm going to go with the alternate. So, is the proportion of men? Oops. What is going on with me today? Is the proportion of men who consume the recommended daily amount of calcium less than the proportion of women that do? Yes. It appears that the proportion of men who get the recommended intake of calcium is less than the proportion of women that do. Yeah, there's pretty significant evidence actually. Something I didn't do that if we had to do this by hand, I can show you. Here, for the men, we found 971 out of the 1900. That means the p hat there would be 971 out of 1900. If you calculate that, and you also calculate the p2 hat as, what, 1548 out of the 2061, and you look at those numbers themselves, you can see there's a big difference between the percent of men who get their daily recommended amount and the percent of women that get their recommended amount, which actually is what leads us to rejecting. They're very, very different. I believe the men, if you calculate that percentage, it's right 51%, and for the women, it's about 75%. So yes, definitely, there seems to be a difference between the genders. And so I have a few examples, a few practice problems of this on Blackboard already that I recommend you do on your own. There's like 4 of them, I think, and then also the practice quiz, of course, has one. But it's really just practicing using StatCrunch. Can you get the numbers from the problem? I underlined them there in our problem. Put them into StatCrunch. That's all I did. Got a p-value, and then when I see that p-value, oh, I know a small p-value means I end up rejecting the null. And the null is always set up that the proportions are the same, that there's no difference between men and women in this case. And since I'm rejecting the idea that the proportions are the same, that means I believe this. I believe that the proportion of men was less than the proportion of women who get their recommended amount of calcium. So I strongly urge you now to go do at least some of those practice problems, just pulling those numbers out of the problem and then setting up the hypotheses, putting it in StatCrunch, getting a p-value, and then making a conclusion. Because that's it. There's no like pen and paper work going on right here. You don't have to bust out a calculator for anything. If you want to, go read up on how to do it by hand. It's not fun. Trust me. I used to have to teach it before we got StatCrunch. All right. So that's hypothesis testing to proportions. And before I close that out, I want to make sure that I make some comments because I kind of neglected to mention some things at the beginning. Note, we can only do this if the following conditions are met. Randomization, independence, and n times p times q is greater than or equal to 10. And we've seen these before, and I mentioned it back when these kind of assumptions started being laid as groundwork. We should always be assuming these in our class, but in real life, this might not be the case, right? I think I even specified in the problem that, yeah, it was random. If it wasn't a random selection, stats can't be used, period. That was a week 1 thing, right? We shouldn't be using stats that are obtained not randomly. Independence. Basically, we want to make sure that the men in this sample didn't affect the women in this sample, right? You don't want to select families at a time and have, let's say the father and the mother of 3 boys, and all of them are in the sample, right? So the father and the 3 boys are part of this 1900, and then the mother is part of the 2061, because they're not independent. They probably eat meals together. They probably get the similar amounts of calcium. You don't want that. You don't want your participants in the sample affecting one another if you can help it. And the last thing, NPQ is greater than 10. You can check it out, but I'm pretty sure with these really high ends, right? How many sampled? Almost 4,000. That's going to be greater than 10 after you take the product. But in small cases, sometimes this isn't true. I mentioned in class before that these things, these conditions are important, but I'm not going to expect you to check them, because if it fails any of these checks, you can't do anything. And where's the fun in that? I have to grade you on something, right? So these assumptions are there, and I want to make sure to mention them, but just you don't have to check them, because they're going to check out, I promise. At least they should. All right, so extending this idea of being able to compare 2 unknown parameters, if one's greater than, less than, or not equal to another, or they the same, for proportions can actually be extended into means as well. And I'm going to jump straight into that, which is 11.3, I believe. We're going to skip 11.2. 11.2 is for dependent samples, where your samples are paired up in some kind of way, which we're not going to do that. We're going to jump straight to what's more likely the case in real life, more often than not, which is inference about 2 means. And I need to mention these are independent samples. for means, if you have dependent samples, there is a way to do it if your participants in the sample affect one another. But we're just going to talk about independent for our purposes. So we can test if two population means maybe I should phrase it this way. We can test if one population mean is greater than, less than, or not equal to another population mean. And the process is going to be very, very similar to how we did it with proportions. That's why I'm not stopping the video, creating a whole nother video for 11.3, because it's going to boil down to the same kind of stuff. We're going to lean on StatCrunch a lot. I think at the top I threw up some notation, I believe, right? Just in case anyone doesn't realize, we're now talking about mu's, right? Mu1 and mu2. And those are our parameters. We'll also have x1 and x2. Those are our statistics. For the mean, right? Oops, they need bars. Forgot about that. But mu1 and mu2, we have a true average for one part and a true average for another part, and then we get statistics on both. The classic example is men versus women, right? How much does the average man weigh versus how much does the average woman weigh? We go out, we get a sample of men, a sample of women. We can find an average weight for men, an average weight for women, but those are our statistics. We will never know what these truly are, really, right? Not only that, we also will be able to produce a sample standard deviation for both. Right? Each sample will have its own standard deviation, then also N1 and N2, which is our sample sizes. So there's going to be some true parameters out there. The average, how much does the average man weigh, and how much does the average woman weigh? We'll never be able to know these, but are they the same? Do men weigh more than women? Do they weigh less than women? I think it's pretty obvious. Men tend to weigh more than women on average, right? So the average man is going to weigh more than the average woman, I'm going to guess. We can go out and get statistics. Maybe I sample 100 men, 100 women. I can find an average weight of men, average weight of women. I can find the standard deviation of those samples I drew, and then also my sample sizes. All right, so let me just jump straight into the steps. So steps to hypothesis test. Two means. First step, set up HO and HA. Shocker, right? HO should be set up that the means are equal to one another. That the average man weighs just as much as the average woman weighs. Okay, we probably know that not to be true. How about the average heart rate for a man while resting is equal to the average heart rate of a woman that's resting? I don't know if that's true. I have no idea. I don't have a medical background, but that's my assumption to start out with. And then HA will involve an inequality. Just like proportions, right? HA could be that mu1 is less than mu2. HA could be that mu1 is greater than mu2. Or HA could be that they're just different. Mu1 is not the same as mu2. There's some difference between them. And again, while we're in this section, spoiler alert, StatCrunch is going to be doing the same weird thing where it likes to have it all set up on one side. So the null in StatCrunch is this, right? It subtracts the mu2 from both sides. For some reason, it likes it shown like that. Same thing for all these other ones. And HA mu1 minus mu2 is just not equal to 0. So StatCrunch likes having everything on one side. It's not a big deal because the signs, they don't flip or anything. You still are going to choose from a drop-down menu, less than, greater than, or not equal to. So it's not a big deal. Step 2. So after you set up an HO and HA, I'm just going to zoom back to my note. What did I say? Step 2 was there. Use StatCrunch. We're gonna take a brief step before we jump straight to StatCrunch. It would be find x1 bar, s1 bar, s1, x2 bar, and s2. What are these? X1 bar is the mean of sample 1. S1 is the standard deviation of sample 1. X2 bar is the mean of sample 2. And S2 is the standard deviation of sample 2. I'm going to put, hopefully, these are given already. But I need to make sure I have a step for it just in case they're not. So after you set up the hypotheses, you need to find the statistics themselves. So I could give you data, right? If I provide the data and ask you to calculate the mean, you know how to do that. You add them all up, divide by how many there are. So I could give you the data for, I give you 10 men's weights. You should know, add them all up, divide by 10, that'll give you your sample mean for the men. If I give you 13 women's weights, add them all up, divide by 13, you would get your sample mean for the women. You guys know the standard deviation formulas too. Way back when, I guess, what is that, chapter 3 maybe, when we did it? How do you find standard deviation? Okay, well, you have to find the mean first. Well, that's good. You probably just did it because you need those as well. Find the mean, and then you take each value minus the mean squared, add those all up, divide by n minus 1, and then take the square root. That's a lot of work, so that's why I say hopefully these are given already, especially because I already tested you guys personally in chapter 3 that you guys know how to do mean and standard deviation on your own. So a lot of times I'm just going to give a problem that already has these listed. There's no reason to do it on your own, but I already know that one of the practice problems I put on Blackboard, I didn't. I gave you the data. I'm going to make you do this yourself. And who knows, maybe on the final exam I'll do the same thing. After you find those, or after you identify in the problem where they are, next step is use StatCrunch. Luckily, we're not going to have to deal with doing this by hand. It's pretty nasty trying to do it by hand. In StatCrunch, go to, well, let me put this on online. Go to Stat, the Stat menu, and then after you click on Stat, you choose t-stats. This is because if we were to do this by hand, we would need t-scores. We would need that student's t-distribution table that you guys already have. After you choose t-stats, you can go to toSample. And then you can go to with summary. Let me just put this on the next line. And then you're going to need to enter your X1 bar, S1, and N1. Also X2 bar, S2, and N2, and then also HA. Say it's very similar to when you're doing it for proportions. You go in, type the numbers from the problem. The only thing is the problem might not give you these four things. I might, if I was being cruel, I guess, make you calculate these four things right here on your own because you should know how to do them, right? You know how to calculate mean and standard deviation. But it's very similar to proportions where you're just typing numbers into StatCrunch and seeing what we get out. And then step 4, report the p-value. And after step 4 is make the conclusion. If the p-value is less than 0.05, we reject the null hypothesis. And if the p-value is greater than or equal to 0.05, we fail to reject HO, the null hypothesis. So it's very similar to the proportions testing for two proportions. For two means, very, very similar. You set up HO and HA. HO is that there's no difference between the true proportion, the true mean for one versus the other subset. The alternates are that one is less than or greater than or not equal to than the other. After that, if I wanted to be a little tough on you guys, I can make you calculate the mean and standard deviation if I give you raw data. A lot of times they're given already though. Then in StatCrunch, you go to t-stats, toSample with summary, and then you enter in all the information hopefully given in the problem or that you just found in step 2. You report the p-value StatCrunch will give you, and then if that p-value is small, you reject. If it's big, you fail to reject your null. Very, very similar. That's why I didn't start a whole new video. So let's go through an actual example of, oops, that looks awful. Example of testing two means at the same time. Since we did one example with the proportions, let me just find a good one. All right, so I'm going to do an example, let's see, about driving to work. All right, yeah. All right, so there are two routes I can take to drive to work. Let's call them route A and route B. Let's see. I randomly sample 30 days of driving route A and find an average commute time of 40 minutes with a standard deviation of 7 minutes. Also randomly sample say 28 days of driving route B and find an average commute time of, let's say, 42 minutes with a standard deviation of 3 minutes. Is there evidence route A is faster than route B? That'll be the example we're doing. All right, so here we go. Let's see. There are two routes I could take to work, and I don't know if anyone remembers, I drive to DC. So these 40 minutes and 42 minutes, that's not really representative of what my actual commute time. But let's say there's two ways to get to work, right? And I randomly sample 30 days of driving route A, that first way of getting to work, and I find that it takes on average about 40 minutes to get to work that way. And then route B, I take 20 days of driving route B, randomly sampling which days too. I want to make sure I put random in there because I don't want, all 28 days to be Mondays or something like that. So I randomly sample 28 days of driving that second route, and I find an average commute time of 42 minutes. And now just by looking at that, 40 versus 42, it does look like route A is faster just in general, right? On average, we took about a very similar sample size, 30 versus 28 days. Route A, it was 40 minutes on average. Route B, 2 minutes longer. But then the standard deviation, it looks like with route A, the standard deviation is much higher than with route B. Meaning some days, remember, standard deviation is how much it varies, right? Some days it might take 47 minutes or 54, right? Those two standard deviations away is what's common or expected or usual, whatever you want to call it. Whereas this route B is definitely more reliable, meaning there's not much variation, right, compared to route A. Route A, some days I was sitting in traffic for a very long time or something. So I want to know if there's a big enough difference between these that I actually am just going to go with route A from here on out, since on average it's 2 minutes faster, or if this is just random. They are about the same. Maybe it doesn't really matter which route I take. So that's what we're going to be doing. All right, so first step in testing two means, to set up hypotheses. HO, HA. HO is that the average time it takes to get to work using the first way versus the second way, it doesn't matter, they're equal, right? That's always going to be the first hypothesis, or the null hypothesis, I should say, right? That the two means are equal to one another. The alternate is that route A, the average time it takes to get to work with route A is what compared to route B? Well, it says faster, which means that the average time it takes is less than, right? It's a less than problem. It doesn't say the word less than, it says faster, but what does that mean? That the time it takes is less than the time it takes for the second route, right? So those are my two hypotheses. Step 2. What was step 2? Step 2 is to find x1 bar, s1, x2 bar, s2 bar. Okay, so let me list all those out. I need x1 bar and s1, and I also need x2 bar and s2. And now this is one of those cases where I actually already provided them in the problem. Oh, maybe I'll highlight them. So route A, I randomly sampled 30 days of driving and found an average commute time of 40 minutes and a standard deviation of 7 minutes. And for route B, Find an average commute time of 42, standard deviation of 3. So let me write those down. Maybe I'll do this. Right, route A, 40 minutes, 7 minutes. The average I found for route A was 40, and the standard deviation was 7. And for route B was 42 and 3. They're just in the problem, right? The sample average I found for the first route was, or route A I should say, was 40 minutes. Its standard deviation was 7. For the second route, route B, I found an average of 42 with a standard deviation of 3, right? And so when I say find these things, and hopefully these are given already, they were in the problem, they're already there. What can I do to make these not given in the problem? I would have to give you all the data. I would have to list out how long it took me to get to work for all 30 of the first days, right? You would add them all up, divide by 30. Apparently you get 40, and you can also find a standard deviation of 7. That would be if I give you the actual data, right? On day 1, it took me 46 minutes. On day 2, it took me 31 minutes. On day 3, that's a lot. I would have to listed the data and then make you guys calculate this, which I can technically do. I don't want you guys to think that I will never do it, because I can make you come up with mean and standard deviation on your own. You've shown that before, but luckily all these numbers were provided in the problem because I'm so nice, right? So they were given. Step 3. Step 3 says use StatCrunch. In StatCrunch, go to stat, tstats, toSample with summary. All right, so go back to StatCrunch. And I go to stat, tstats, toSample with summary. And similar kind of pop-up window comes up as when we did proportions, right? So I have to enter all the stuff I need in here. So for sample 1, what was the sample mean? I believe it was 40. It took an average of 40 minutes. The standard deviation on that was 7. And how many days did I sample? 30. Right? The first sample, I found an average of 40 with a standard deviation of 7, not 70, 7 with a sample size. I sampled 30 days. In the second sample, the second route, route B, I think it was 42 was the average. The sample standard deviation was only 3 there, and the sample size was 28. Right? Zoom in a little bit so you guys can see. I'm just entering the numbers in from the problem. Don't have to tinker with anything. I just need to set up my HA. It's set up with not equal to right now, but we want to know if the first sample for route A produces a faster route, which means it takes less time. So I'm going to choose less than and hit compute. And here we go. My p-value, it says, is 0.0802. So go back to my notes. I entered in all that information, right? Maybe I'll just write step 3 was done. Step 4, what was the p-value? It was 0.0802, I believe. Hold on, let me just double check. I always get worried. Yep. P-value is 0.0802. And step 5 is to make my conclusion, which the conclusion is anytime we get a p-value, you should always be comparing to 0.05. Where is my instruction? There it is. If the p-value is less than 0.05, we reject. Greater than 0.05, fail to reject. So my p-value was 0.08. So since my p-value 0.0802 compared to 0.05 is bigger, right? Ooh, that's not a good looking greater than sign, but greater. Oh man, what is wrong with me? Greater. Was greater than 0.05, right? 0.08 is greater than 0.05. We fail to reject. HO. This means what? This means that, well, going back to what my hypotheses were set up to be, I'm not rejecting this. I'm keeping it. I'm retaining it, whatever you want to say. But I I'm not rejecting this. I'm not going with the alternate then, because I'm not rejecting the null. I'm keeping the null. So since I'm retaining the null or keeping the null, this means that the average commute time between route A and route B are likely the same. They're equal. Right? I'm keeping the idea that these routes are the average time it takes to get home or to work is the same. That they're equal. I'm not going to go with the idea that one is less than the other, even though my statistics seem to have suggested it, right? That this way was faster than this way. It was 2 minutes faster. But I'm guessing this high standard deviation is why it's not a guarantee that one route is faster than the other, because some days I'm going to be sitting in traffic here a lot longer than here because there's more variation. Or maybe I just need to sample more days. Maybe sample 350 days for each driving route, but that's a lot of work. I don't know who would do that. But hypothesis testing wise, it looks like the average time it takes to get to work is the same no matter if I take route A or route B. Now, if I change the problem and make route B, it take 84 minutes, don't change anything else, 84 minutes here, 40 here, that's going to end up in a rejection. I already know that because that's going to be significantly faster, right? It takes me twice as long. And you can check it. If you change route B to be an 80-minute drive, keep everything else the same, you're going to end up in a rejection. Because, in that case, you don't even need statistics to prove that. If it took 80 minutes with route B, 40 minutes with route A, no one's driving route B. They're always going to be driving route A, right? But in this case, it was a little dicier because, you're only saving 2 minutes. There's more variation with that first faster route. So actually, it's not faster in the long run. It's about the same. I strongly recommend now going and doing those practice problems that I have posted to Blackboard. There's 4 of each of these. 4 hypothesis testing to proportions, 4 hypothesis testing to means. There will not be, how do I put this? There won't be a question on exam 2 about this stuff because it's being taught right before exam 2. So I want to give you guys some time to digest it a bit. But on the final exam, yeah, sure, why not, right? And definitely there's going to be a quiz 9 about this, so make sure you get it done. I forgot to mention there are also kind of assumptions made when we're doing hypothesis testing to proportions as well. That it's random, that they're independent, also that your sample size is big enough, and big enough depends on the situation. Sometimes they say just make it greater than 30 like we do with central limit theorem, but it depends on the situation. And we had 30 and 28 for this one, which is pretty close. So I will end there. Make sure you try the practice problems for these because it's really just navigating StatCrunch menus. Steps is the stat program I use at Census. StatCrunch is what I use with you guys. So it's just kind of figuring out StatCrunch, knowing how to use those menus. I guess you do have to know how to set up the hypotheses. You have to know what to enter into StatCrunch, but it does all the work for you to get that p-value, and then you use the p-value like we did with correlation and regression and hypothesis testing one proportion. If the p-value is big, we fail to reject. If it's smaller than 0.05, we reject the null. So that is all. Please, please, please try the practice problems. And that's it.